Lecture 1.2, Echelon Forms of Matrices. Definition. A matrix is said to be an echelon form if the following three conditions are met. All non-zero rows are above any row that has only zeros. In other words, all the rows that are all zeros are down at the bottom. Each leading entry, which means the first non-zero entry in a row, so you might have 0, 0, zeros and then come to a non-zero entry going from left to right. In that first non-zero entry is in a column that is to the right of the leading entry of the row above it. So as you go to the next row, you got to go over to get to the first non-zero entry. And all entries in a column below a leading entry are 0. All right, so let's put these three up here tops and let me draw a little picture for you here. So I'm going to start with a matrix, and here's the first row. That asterisk will mean a non-zero entry, and then the dash line means maybe some of those are 0 or some of them are non-zero, right? Then the next line, we got to move over to get to the first non-zero entry, the first asterisk. And then another one, we move over again. And so look, we just have zeros down here. And you can see that we have kind of a stair-step fashion going down the matrix, down and to the left. And we're also getting this lower triangle of zeros, which you should be somewhat in memory of. All right, so let's do a couple of examples here. So in this example, I got a row of zeros, that third row right here. That is, oops, I'm writing in black. All right, let me change here and write in, what would be a pretty color? How about, this is maybe the same color that the type is in. Yeah, that row of zeros is above this row down here, which has non-zero entries in it. So what we need to do, of course, is we need to do a row operation to switch that around. Now it's in echelon form or row echelon form, where that row of zeros is at the bottom. And you see the stair step, right, sort of thing going on there with this lower triangle of zeros. This lower triangle of zeros right here. Not a great triangle. And I got, of course, got this extra 0 over there, which is no big deal. It just that happened that I got an extra 0. Let's do another example. In this example, we don't have any rows that are all 0, but we have an example here where the leading entry in this row is, oh, pardon me, that's not the right one. Forget that. It's up here. The leading entry in this row lies to the left of the leading entry in the row above it. And it can't happen. It has to lie to the right. So again, a simple row interchange will take care of that, right? And so now we interchanged rows 2 and 3. And again, we have that lower triangle of zeros and this, what I like to think of as kind of stair step going down with the non-zero entries there. Okay, one more. All right, again, we have a leading entry here that does not lie to the right of the leading entry above it. Okay, so this time I can't interchange rows to make that go away, but clearly I can do a row operation. I can take 3 times this row and add it down here to this row, and that should eliminate that -6. And when I do that, I get that, and you can see I have it in row echelon form again. All right, so clearly we can put a matrix in echelon form, which, as I've already been saying, sometimes called row echelon form, by the row operations we learned about in lecture 1.1. And we're going to come back and talk about that more later, how to do that in a little bit more kind of a stylized or standardized fashion. I do want you to note one thing: the echelon form of a matrix is not unique. Here's a quick example. Let's put this matrix in echelon form by doing row operations. Obviously, I'm going to take multiples of the first row and add it down to get zeros below this one right here. And when I do that, I get that. And then I'll just take this row times a -1 and add it down. and that'll give me that, all right? And I have a nice row echelon form, right? Certainly I got that nice stair step thing going down with the non-zero terms, but there's nothing that says I can't do another row operation, maybe and divide this row right here by 2, and if I do that, I get that. And that is also a valid row echelon form. So the row echelon form of a matrix is not unique. What you're looking for, like I said, is that sort of stair step. Whoops, went on the wrong side there. Sorry, like that. All right. Yeah, both are echelon forms. Okay, so how do we put a matrix in row echelon form? Well, like I said, it's basically just doing those row operations, but I want to make it real standard so we have a way that we always know how to do it. So I'm going to have a couple of definitions first. A submatrix of a matrix is the matrix obtained by deleting one or more rows or columns from the given matrix. And this definition will be useful for us now and later as well. So I take a matrix and just suppose we delete the first row and the second column of this matrix. What's left is the 4, 6, 7, 9, right? So I end up with just that submatrix 4, 6, 7, 9. Okay, easy enough. A pivot position, next definition, is the position of a leading entry in a row when the matrix in question is in echelon form. So going along that stair step, we have those things that separate the non-zero from the zero. Our terms are right here. Those are our pivot positions. So I don't need to actually draw anything there. I just say those are our pivot positions, right? Okay, and a pivot column is a column that has a pivot position in it. All right, so it's assumed that like right in here I got zeros, right? So this would not be a pivot column right through here, right? But here's a pivot column right here, and here's one, and here's one, right? Okay. Now, how do we put a matrix in row echelon form? Well, as I said, we're just basically going to put it in triangular form, but I want to be a little more specific there, and I want to use the terms and ideas that we've just developed. So here's the procedure. We begin by finding the leftmost column with a non-zero entry in it. This column will be a pivot column for the matrix. So we look at the matrix and we take the leftmost column that has a non-zero entry in it. And almost always that's going to be the leftmost column of the matrix. And we interchange rows if necessary to put this non-zero entry in the first row. So I want a non-zero entry up there in the upper left-hand corner. This position will be your leftmost pivot position. Now what? Use row operations so that the entry in this position creates zeros in the column below it. And I say we call this entry that is in the pivot position and used to get zeros below it a pivot. So we take this first pivot and we take row operations and we get zeros below it. Okay, now what? We have put a pivot in the first row and the column below it, which I said is probably going to be the first column, is all zeros. So we've kind of done the very first thing we need to do. Now all we do is look at the submatrix obtained by deleting the row and column that the pivot is in. All right, so we just throw out that, and what we'd be starting off is probably first row, first column. We just throw it out. We don't have to write it like that row and column aren't there, but we just ignore that and look at the submatrix we get, and we just repeat. We just do the whole thing over again, and we keep going like that, and eventually we'll get to where there are no more pivot columns. We'll walk across the matrix, and the result will be that we put the matrix in echelon form. So let's do an example. Put the following matrix in row echelon form. So there's the matrix. I got this big, 5 rows and 5 columns. We call that a 5 by 5 matrix. All right, so I think what I'm going to do is, put it up here in the corner and have my rows labeled. So look, here is my first pivot column, of course, right here, because I have some non-zero entries in that first column. So I don't like the fact that there is a 0 up here, though. So what I'm going to do is I'm going to interchange one of these rows that has a non-zero entry in that first column with that first row. And I think I interchange row 4 and row 1. Yeah, row 4 goes to row 1 goes to row 4. All right, so I now have my pivot right here, and of course I'm going to use it to get zeros there, there. I already have a zero there, so I don't need to do anything, and then I'm going to get a zero there. And I'm just going to use multiples of the first row added down. So look, here's my first row right here, and then I'm going to use multiples of it added down. And so what do? I just take row 1 plus row 2 and replace row 2, and that gives me a 0 there. I take negative 2 times row 1 and add it to row 3, and that's the new row 3, etc., etc. Row 4, I didn't have to do anything. Okay, now what? Now I look for my next pivot column. All right, let's go to the second column. Is this a pivot column? The answer is no, because this column, the second column, is not pivot, because the only non-zero entry is up here, and it's behind this non-zero entry, right? So it's not a leading non-zero entry. So I go over to the next column, and lo and behold, there you go. I have a nice pivot position there. I have a pivot, so I'm going to use multiples of row 2 to get zeros here and here, and then I don't need to do it down there, so let me do that, and I'm down to there. Okay, so if you run through that, you should be able to get this. Of course, you should have paused me and should have worked this through yourself. If you're still a little bit confused as to what's going on, then that's okay. But for most of these exercises, you should be pausing me and doing them yourself. Where's the next pivot column? So we have a pivot column here. That doesn't change. We now have a pivot column here. Look at the fourth column. The only non-zero entry sits behind, so to speak, to the right of other non-zero entries in that row. So that's not a pivot column. We come over here to the fifth column, and certainly I see some non-zero entries that have only zeros in front of them. So I think I'm going to use, there's my pivot position. I'm going to use that as a pivot. So I'm going to take multiples of row 3 and add them down and wipe out the zeros below. And look at that. I have a stair step, if I can draw without messing things up. There's my stair step, right? And there's my lower triangle of zeros with some extra zeros to boot, okay? So we've succeeded in putting that in row echelon form. A matrix is said to be in reduced row echelon form. This is very important. If it is in echelon form and the following 2 additional criteria are met. So we put the thing in echelon form, but then we do some other things to it. And the first thing we do is we make each pivot position have a 1 in it. So all those non-zero entries, we just got to turn them into 1s. And then what? Then each pivot position has the only non-zero entry in its column. So we don't just want zeros below the pivot, we now want zeros above the pivot. So look what we have here. So I've gone back to kind of a generic matrix in echelon form, or row echelon form. I now want to put it in reduced row echelon form. So the first thing I need to do up here, number 1, is make each pivot position have a 1. So how will I do that? I will take this row and divide it by whatever this non-zero entry is. I'll take this row and divide it by whatever this non-zero entry is. I'll take this row and divide it by whatever this non-zero entry is. And the result is that I will get 1s there. I have to do this with legitimate row operations. All right, so I divide the whole row through, and I now have all 1s there. Okay, but if you look, I have now, some generic thing up here. It might be 0, might not be 0. I have generic things in this column up here. I have zeros all down here, right? So that's good, but I need to get zeros above my pivots. So the next thing to do is to take a multiple of this row and add it up as needed to the rows above it, different multiples to get zeros where I've indicated, and then I'll take a multiple of this row and add it up to get 0 above it. And so I do that part and I get my zeros, and there I go. I have the thing in reduced row echelon form. I just have 1s down that stair step and zeros both above and below those pivots. And the reduced row echelon form of a matrix is unique. This is important. This means I give you a matrix, you put it in reduced echelon form, 20 different people could put that in row echelon form, just regular echelon form, and there could be 20 different correct answers. But if you go through the rest of the way and get your ones where they need to be and your zeros above, it will turn out that there's only one way to do that correctly. If you do all the row operations, you will end up with the same matrix if you do them all correctly. So there's only one reduced row echelon form of a matrix. That's what I mean by saying it is unique. Let's do this example. Let's put the following matrix in not A, but in the reduced row echelon form, right? There is only one, so we use the definite article, the. Okay, this is the matrix we worked with before, so we already put it in echelon form, and there it is. So we just have a little bit more work to do. Remember, there's our pivot, and there's our pivot. So what we're going to do is we're going to start off and we're going to go, instead of from left to right, eliminating, we're going to go from right to left. So we're going to start with the rightmost pivot. So I've made that green, and down here, there it is, the rightmost pivot, and we're going to make it a 1. And so we just divide through by 2 and get a 1. All right, now we have that 1. Now what we will do is we'll use that pivot again, there it is, and we'll get multiples of row 3 to eliminate the non-zero terms above it. And there's only that one right there, right? So of course we'll take -2 times row 3, add it to row 1, and that's the new row 1. Right, we are done with that column. Now we're going to move over to this pivot, and look, it's already a 1, so I don't need to divide by it. So the next pivot over is already a 1, so we're going to just take a multiple of row 2 and add it upwards to get a 0 above it. So we'll use it to eliminate that non-zero term above it, so you can see. So we do that, and we get a 0 there. Let's see what we have. We have our pivots right there, which all have become 1, and we have zeros above and below all those pivots. It looks like maybe we're done. Since the last pivot, which I show there in green, is already a 1, we are actually finished. There is the reduced row echelon form of that matrix. Okay, if we put the augmented matrix of a system of linear equations in echelon form, we can solve the system through back substitution. We've been doing that, right? We've been taking a matrix and putting it in triangular form, which we now understand we call row echelon form, and we can solve through back substitution. We've already been doing that. But if we put it in reduced row echelon form, we actually can read the solution directly from the matrix, even in the more complicated situation in which our system has infinitely many solutions. If you remember, a system of linear equations can be inconsistent, meaning it has no solution, or it can be consistent, meaning it has a solution. The solution set is not empty. And in the case where it's consistent, you might have one solution, or you might have infinitely many solutions. That's what I talked about briefly last time, and we'll see that a little bit more here. But, and in fact, we're getting to that now because we will see that the reduced row echelon form allows us to read off the situation pretty easily. So here is an important fact that we will use. If the rightmost column of the augmented matrix, which means the one corresponding to the right-hand sides of the equations in the system, right? When you set up the augmented matrix, that rightmost column, that's all the right-hand and sides of the equation. If that turns out to be a pivot column, then the system has no solution. And I say, oh, why is that? Well, it's not that hard to figure out. In a row echelon form, there would be a leading non-zero term in the last column. So there would be a row that had all zeros except in the last column. So you'd have a row like that, right? All zeros, might be a big matrix with lots of zeros, but the very last column has a non-zero number. What does that mean? That means it's the equation, if you think back in terms of the system, that says 0 equals whatever that non-zero number is, which is impossible. Thus, the system would have no solution. So this is a big deal. This is something to remember. If you're looking at the augmented matrix of a system and you do whatever you do to start doing row reduction on or putting it in row echelon form, and you discover that the last column is a pivot column, there is no solution. If the rightmost column is not a pivot column, then the system is consistent, which means it has a solution. And why is that true? Well, first, let's think about the case where every column except the last column is a pivot column. So you put it in row echelon form, and you have a pivot in every column except the last one. In this case, the reduced row echelon form allows us to read the unique solution straight from the matrix. So we have a unique solution, and we can read it straight from the matrix. So look at this example. Suppose this is actually already in reduced row echelon form, but you can see I have a pivot here, 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 but none in the last column, right? Okay, so I have a pivot in every column except the last column. You can easily see, well, I say the matrix is in reduced row echelon form. Every column except the last is a pivot column, and it's easy to read right away from the first row. X1 equals 7, right? X2 equals -3, etc. X3 is 2 and X4 is 9. So I can easily see if every column is a pivot column except the last one, I have the thing solved if I have it in reduced row echelon form. All right. Now suppose the rightmost column is not a pivot column and one or more other columns is not a pivot column either. In this case, it'll turn out that there will be infinitely many solutions, and the reduced row echelon form gives us an easy way to write a representation of that infinite solution set. So in order to see this, we need a definition. In the augmented matrix for a system of linear equations, a variable that corresponds to a pivot column is called a basic variable. So if I have the augmented matrix and I put it in echelon form or reduced row echelon form to where I can see where the pivots are, if I have a pivot column, the variable associated with that is called a basic variable. So what do I mean? I mean, for example, if the third column were a pivot column, that would be saying that x sub 3 would be a basic variable, since that's the variable that's represented by all the numbers in that column, right? The coefficients on x3 are those numbers. All right, so x3 is what we call a basic variable. A variable that corresponds to a column that is not a pivot column will be called a free variable. And we'll see why in a minute. We will see that the free variables will give us a way to represent the solution set of the system based on information we can gather about them from the reduced row echelon form of the augmented matrix. So having a reduced row echelon form will give us just what we need. And so let's take an example here where we have a pivot in the first column. We have a pivot in the second column, and we have a pivot in the fourth column, right? You should be able to see that we do not have a pivot in the third column or the fifth column or the sixth column. Okay, that's good. So the pivot columns are 1, 2, and 4. The sixth column not being a pivot column, assuming this is an augmented matrix from a system, that means that there is going to be a solution. And in fact, I say here that pivot columns are 1, 2, and 4. Thus x1, x2, and x4 are our basic variables. The variables that correspond to non-pivot columns, x3 and x5, are our free variables. It's easy to see that this system is consistent and has infinitely many solutions. Here's why. Any values picked for the free variables will allow us to solve for the basic variables and arrive at a solution. For example, look at row 2. If I pick a value for the free variable x3 and the free variable x5, I can then solve for the basic variable x2, correct? So it doesn't matter what I pick for x3 and x5. I'm going to be able to solve for x2 because that's just an equation, right? Row 2 is representative of an equation. And if I plug numbers in for all but one of them, I can solve for that one I didn't plug in, right? And that's what we're going to do here in a second. So the free variables really are free in the sense that each one can take on any value Once the free variables have values, the value of each basic variable is determined by the equation it is in, right? So from the first line, let's go through this. We read that x1 is just equal to 2. All right, there's nothing free about that very first equation. X1 just has to be 2. From the second line, we read x2 plus 3x3 plus 2x5 equals 8. Make sure you see that where that came from, all right, as I was just saying a little bit earlier. So if we solve for x2, we have that x2 equals 8 minus 3x3 minus 2x5. So put in your favorite values for x3 and x5, you know, 1 and 0 or something like that, and you get a value for x2. Put in different values for x3 and x5, you get another value for x2, etc., etc. From the third line, you should be able to see that that's x4 minus x5 equals negative 3, so we can write that as x4 equals x5 minus 3. Now, whatever value you've picked for that free variable x5, you have what it is, you have the value for x4, all right? So the last two lines, of course, just say that 0 equals 0, and they offer us no new information. If they had non-zero terms after things being put in reduced row echelon form, we would we'd be able to nail down more and more. We wouldn't have free variables. We'd have a unique solution, but we don't. So those rows of zeros in this case give us some freedom, give us those free variables. So look, we can write the solution set like this as a set of ordered, you know, not ordered pairs, it's ordered 5 tuples, right? So the very first one, x1 has to be 2, so you can see. And then the next one, x2, is right there. It's written in terms of the free variables, 8 minus 3x3 minus 2x5. And then x3 is just called x3 because it's free. x4 is then what we solved it to be, x5 minus 3, and then x5 is just what is chosen to be. So, and then I say here, this is important to understand, I'm saying x3 and x5 are elements of the real line. They are the set of real numbers. That symbol means element of, or is a member of the set, and that of course means the set of real numbers. So I'm saying you are free to pick any values you want for x3 and x5 and plug them all in here, and you will have a 5 tuple that solves the system, right? So if you pick 0, 0 for x3 and x5, what do you get? You get, read it with me, it's 2, 8, 0, negative 3, 0. There's a solution. Put in 1, 1, and you get, I think, 2, let's see, 8 minus 3 minus 2 would be help me out, be 3. So you get 2, 3, 1, 1 minus 3 be negative 2, and then 1 again. There's another 5 tuple, right? So we can do this all day by choosing different x3 and x5. All right, and I say here, note how our solution only involves explicit mention of the free variables. That's the whole point. Once we, those have to be in there because we have to pick values for them, but then the others, x1 and x2 and x4, are written in terms of those free variables. We will find it useful to write the n tuples vertically. That is how we will be writing vectors. If you know what a vector is, great. If you don't, you're going to learn. So in other words, you might rewrite it like this. We'd have a big, big set brackets, and we take that ordered 5 tuple and write it downward instead of left to right. So it's the same thing, just written vertically. And I think it's a little easier to read than that 5 tuple on the previous page. In fact, what I like to say is that the solution above is in parametric form, meaning that each variable above is expressed in terms of 2 variables called parameters for the solution. Those 2 variables, of course, are x3 and x5, and everything is written in terms of those 2 variables. To emphasize this, we often give different names to those free variables, names unrelated to the variables in the original system. So we might write the above solution like this. I use s and t now. So x1 is 2, x2 is 8 minus 3s minus 2t, x3 is s, x4 is t minus 3, and x5 is t. So you can see I've made x3 into s and x5 into t. And that's kind of nice because now we just have these parameters s and t, and they tell us what each x value is, right? x1 through x5. Of course, x1 is just always 2. Each variable is represented in terms of the parameters s and t, both of which are free to take on any real number value. So to summarize what we've done so far, let's outline our method for finding the solution set of a system of linear equations. Form the augmented matrix of the system. Put the augmented matrix in row echelon form. So just do the row echelon part. Don't do reduced row echelon first. Now you have to do row echelon first, but don't jump to reduced row echelon, because once you've done that, you'll be able to see your pivot columns. If the last rightmost column is a pivot column, the system is inconsistent and you are finished. That's the case if you have an augmented matrix for a system. That right column can't be a pivot column. If it is, you're done because it's inconsistent. If the last column, excuse me, is not a pivot column, the system is consistent. So go forward and put the matrix in reduced row echelon form. So finish it out and put it in reduced row echelon form. And what you'll find then is if every column besides the last column is a pivot column, then there is a unique solution. The solution set will have one point in it, one 5-tuple or one ordered pair or one ordered triple, whatever you're working with. There will be just one unique solution, and it can be read directly from that reduced row echelon form. If there are columns besides the last column that are not pivot columns, should say not. that are not pivot columns, these will correspond to free variables, while the pivot columns correspond to basic variables. For each basic variable, there will be a row that gives an equation within which you can solve for that basic variable in terms of the free variables. So do that and write your final solution in parametric form. All right, let's do a few examples and then we'll be done. Solve the system. I don't know why it's green, but it is. So what do we do first? We get the augmented matrix. So what I say to you, yes, pause and do it. Anytime you see something here that, oh, I think I can do that, stop me and do it first, right? And you'll be looking at the notes, I hope, that you have for this, and you should have space to pause and do it. So I hope you've been filling out those notes as we've gone through this. And now's your chance to work this problem. All right, so I'm pausing, letting you stop and do it. All right, off we go. Augmented matrix. I hope you can see that's the augmented matrix, right? 1, -2, 8, 29 is that first row. That's the coefficients in the first equation, et cetera, et cetera. So we put it in echelon form, row echelon form, and again, I'm not going to go through the details, but there we go. We have a pivot in the last column, right? No need to go further. Last column is a pivot column, so the system is inconsistent. We're done. The answer would be empty set for the solution, right? Next example, pause and do it. 2 equations in 2 unknowns, so pause and do it. Okay, on we go. Augmented matrix is there. Put it in row echelon form, a row echelon form, and I see that the last column is not a pivot column, so I should proceed. So it's consistent. So let's put it in reduced row echelon form. I'm going to divide that second row by 2 to get a 1 in my pivot position, then use a multiple of that second row, add it up onto the first row to get a 0 above it, and there's what we end up with. So we have the matrix in reduced row echelon form. Every column is a pivot column except the last one, so we have a unique solution. X1 is -5, X2 is 4. And we can write it like this, a single point solution set, right? The ordered pair -5, 4 inside set brackets. There's the solution set. One more example, so pause and solve this one. Pause, okay, off we go. Augmented matrix, put it in row echelon form. The system is consistent. We have pivots only in the first 2 columns, right? Last column isn't a pivot. So we finish up and put it in reduced echelon form. And it looks like the columns 1 and 2 are pivot columns. So there are basic variables, X1 and X2. X3 is free. So the first row tells me that X1 is equal to 2 minus X3 if I solve it. And X2 is equal to 5 minus 3X3. So I have taken each row and taken the basic variable and solved for the free variable, right? So I have those solutions. So in parametric form, our infinite solution set is 2 minus 2t, 5 minus 3t for t, an element of R. So again, plug in your favorite values of t and you will get ordered triples that solve the system. You can just go check that if you want. plug in, t equal 0, then try t equal 1, then try t equal -5, etc. Try those values and stick in and get what the ordered triple is for each and plug them in up here, and you will see that they each solve the system. So we do indeed have an infinite set. And we will stop there.